All right, good afternoon. This is our last lesson on magnetism, on magnetic flux and Faraday's law. Last day we were kind of looking at induced EMF and generators. And what was a generator again? It was you finding something that was moving generally, or you take potential energy from maybe gas or something and you create movement, and then that movement turns the wire in a magnet, and then that movement of the wire produces an EMF or a voltage in a wire, which would then in turn produce a current. So that's what we went over last day, and what we found out was our voltage that would be induced would be how strong our magnet is times how fast we're moving that wire times the length of the wire times sine theta. Alright, so that's what we learned last day. You could change this if you were talking about a motor or an armature where there would be kind of two wires or a loop of wire, and you're spinning it instead of moving it in the magnetic field, and you'd end up getting 2 times the number of loops of wire times BVL sine theta. So very similar to that. So now let's go into this new lesson. It's called Magnetic Flux and Faraday's Law. And we talk about Lenz's Law as well. So magnetic flux is the area of the coil multiplied by the perpendicular magnetic field strength to the coil. Okay, so we just need to know kind of what this flux symbol, or it's called phi, which is like theta, but instead of the line going sideways, it's going up, is equal to the magnetic field strength times the area of your loop of wire times this time cos theta. So an example here is if you have a magnetic field going through like so, and say you have a loop of wire. I'm going to try to draw it so that it's easy to see. I'm trying to draw it 3D. So it's kind of still hard to see, so I got to show that this wire is closer to us by making it thicker, and then that part of the wire is further from us, that's why it's skinny. So this is a loop of wire. Say if it was an armature, it would go out. But it's kind of a plane, so you have arrows going that way, and then you have your plane kind of like that. So the axis of the plane, or the plane is perpendicular to the arrows, and the axis of the plane goes out like that. So I'm going to draw just the axis here, put a circle in the middle of it, and show that it's going out in the same direction as the field itself there. So this flux here would be the magnetic field times the area of the loop here, which would be just the length, times the width in this loop because it's a rectangle, times cos theta. And what's theta? It's the angle from these arrows here. So you can see our axis here is in the same direction as your magnetic field. So your theta would equal 0 degrees because it's in the same direction. And the plane is perpendicular to the arrows, but its axis is in the same direction. So its theta would be 0. And cos of 0 is 1, so our phi would just be B times A. And that would be our max flux, whatever this flux is. It would be our max when your wire looks like this, when it's kind of perpendicular and its axis is in the same direction as the magnetic field. So that was case 1. Case 2 is if you take, say the field's going this way, and you take your plane and you rotate it like that, now the axis is going straight down, or it's going perpendicular to your field lines. That's when your angle would be 90. Okay. Another example of that is if I turned it like that. Then my axis is coming towards us, which is still perpendicular to the magnetic field lines. So that would be case 2, both of those, where your theta is 90 degrees. And if cos theta is cos 90, that makes that 0, and 0 times anything is 0. So that means your flux is 0 in that case. So you can tell if you span this plane or this wire around in circles, you keep alternating between BA and 0. It would keep alternating. It would really alternate between BA, 0, negative BA, 0, and then back to BA. But that's not that important. So we have a plane here, which is BA. If it's anywhere in between those two cases, then it would have to be this equation, B times A times cos theta, or whatever theta would be. And here's another picture. Here's the one kind of in between. Here's the one kind of in between. And then this one you can see is straight perpendicular to the field lines. So it would be just 0. Okay? All right. So that's what magnetic flux is. They made up this term. It's what flux is. It's just magnetic field times the area of your loop. The loop could be a circle, then it wouldn't just be length times width, but generally it's a rectangle. And then this led to this famous Faraday's law of induction, which I find a little confusing, but it's saying your voltage or your EMF is equal to how many loops you have times your change in flux over your change in time, or essentially meaning how quickly it's turning. So here we can see that we already have an EMF value that we found last day. If you're moving a wire, it's just 2 times the number of loops times the magnetic field strength times the speed times the length of the wire times sine theta. But in this case, you can find it another way, still the same thing, but you can find it another way by going the number of wires times the change in flux, which is this, over the change in time. Okay, so it's kind of the change in the area in relation to this magnetic field over the change in time. Okay, since it has a cos theta, you can kind of think of it as phi is equal to your B times your A times the change in cos theta. Just when it's turning like that, you can kind of think of it like that as well. So you know it would go in between BA and 0 as it spins. So this magnetic flux uses the units called Weber, which is WB, which is the same as a Tesla meter squared, because we know it's just B times A, right? And area is meter squared, and then B is Teslas. And then N is just the number of loops of wire that you have in, say, your armature. So that's the Faraday's law of induction. We'll see an example of how to use that right here. But it's pretty complicated. It uses calculus deep, like in its roots, but we're just kind of seeing how to use the equation. Again, it's the same thing as we learned the last day. It's the voltage that's made in the wire depending on how quickly this flux is changing, really, right? And the faster the armature moves, the faster the flux is going to change, right? The faster it's going to change from BA to 0. So the faster it rotates, the faster it changes. But another way is, say if you had your plane in there and you weren't moving the armature, you just left it still. If you decided, or you were able to change the B value, or the magnetic field itself, then you'd be changing the flux as well. So you don't necessarily have to move the armature. That's usually what we talk about. But you can also just turn on and off a magnet, or say an electromagnet, and that would change your B value really quickly. which would change your flux, which would change your voltage. Okay. All right, so now let's go into Lenz's law. It just says the polarity of the induced EMF will always be such that it will produce a current whose magnetic field opposes the changing flux that produce the EMF. So that might just seem like a lot of words. I think it's better explained on the next page when we get to it. But essentially, say you have a motor, you put a voltage in it and it causes the armature to spin really fast. That spinning motion causes a change in flux, and then in turn puts a voltage back in the wire that is the opposite direction of the voltage that you first put in. So essentially there is an opposite voltage charge that happens when you make movement. Okay, so an example here is Lenz's law. So say you don't have a current in this wire and you move this magnet inside the wire, or you move it in this direction here. Since you're moving the magnet in this direction, Lenz's law says that the magnetic or the current that's going to happen in this wire has to make a magnetic field that opposes that movement. Kind of like Newton's third law, but you have an arrow that wants to oppose the direction of your magnet's movement or its field lines. So you move it this way. This will cause kind of a north pole wanting to go oppose that motion, which means your current would have to go this way, because right-hand rule says if it's that way, the current has to go that way. So essentially you don't have to memorize all this, you just have to know that generally if you have movement of a magnetic field near a wire, the current will happen. It's either going to go this way or it's going to go the other way. It's going to go this way due to Lenz's law because it wants to make a north pole opposing the north pole of the magnet. Okay, I know it's very confusing, but you don't really have to dwell on Lenz's law for what we're going into. Okay, let's look at a sample question. A circular loop of wire of radius 2.5 centimeters. So it's circular 2.5 centimeters. Is in a magnetic field of 0.4 T Teslas. If the loop is removed from the field, so you got your field, it's in the field right now. If you take that wire and you remove it from the field in 0.05 seconds, what voltage will be induced in that wire? Because you're changing the magnetic field, you're changing the flux, because you're going from a magnetic field of 0.4 to essentially 0. You're changing that field, which changes the flux, which makes a voltage in the wire. So let's look at this question. We're going to have to go, the average voltage that's applied is equal to this equation, so it's negative N delta phi over delta T. So we know that average voltage is going to be the number of wires. Let's see, it just says one circular loop, so it's going to be negative 1. The change in phi, we don't know. It doesn't tell us what Weber units it is, so we're going to have to go a little more deeply. Flux is BA cos theta, so it's going to be change in BA cos theta over the change in T. That means our average EMF is going to be negative, let's see, our B value, our change in B value is 0.4 T, so it's going to be 0.4. Our area is pi r squared. And then cos theta, this time it's, we're going to assume that our circle, should have this in the question, assume axis is parallel, kind of like this here. Assume the circle is like this, where your theta is 0. because then our cos theta would be cos of 0. And then our change in time here is just, they give us this 0.05 seconds. And then our average EMF is now negative 0.4 pi. Our R is 0.025 because we need it in meters. Cos 0 is just 1. And then we have 0.05 there. So now we just have to plug that all into our calculator, and I get an EMF of negative 0.0157 volts. So just quickly moving that loop out of that field will give you a voltage in the wire. Alright, now on to the next page. So now we're delving into a motor. What is a motor again? It's the opposite of a generator. Generator, you move the wire to create a current. This time you're putting a current in the wire, and then it creates movement. So let's go through this. In a motor, a current runs through the armature or the loop in a magnet, north-south, in that magnetic field, which causes it to turn. Because we know if there's a current, it'll produce a force on this wire, up and down, which will cause it to rotate. This turning causes a magnetic flux change over time. Because it's spinning, that cos theta is changing, which causes your area or your flux to change over time. So this flux causes an EMF, or a voltage in the wire. Okay, we're already putting a voltage in the wire, but this causes another voltage in the wire just because of the movement, okay, which is counterintuitive. This EMF voltage created from the movement directly opposes the original current provided. It might not be the same value, but it's the opposite direction. Okay, so if you have a current going around like it's showing, the movement of the armature would cause an opposing kind of current, or a opposing voltage, due to the change in flux. This is called your counter EMF or your back EMF of your motor. Okay, your counter EMF or your back EMF of your motor. So overall, the source EMF must be the sum of the back EMF, internal battery resistance drop, and armature resistance drops. So I know this part for some of you might be very confusing due to the fact that in Physics 11 we covered circuits, and you might not have covered circuits in Physics 11. But I won't dwell too much on questions like this, but overall source voltage is equal to your internal resistance voltage drop plus circuits resistance drop plus back voltage. So that just seems like a lot, so let's draw a little picture. Alright, so if I have a battery here connected, every battery has some sort of resistance, and that's called internal resistance. So I draw a little resistor there, and I'll draw a box around it to show that that's the battery. In this circuit right here, this circuit goes around to the armature. We're going to show the armature just as a resistor, because that's kind of what it is. Every wire is essentially a resistor. Wires generally won't have much resistance, but this is the resistance of this armature. Okay, if you have more turns, it'll probably have more resistance, but that's our resistor. And then it comes back to our battery. Okay, the initial power of this battery that we're giving to the motor is called the source EMF, okay, or your source voltage. And then this here is kind of your voltage. I'm going to put a little I. The voltage is going to drop a bit because of this tiny resistor in here. Okay, and that's your. Actually, I should do tiny r. I'm going to do that. Tiny r. That's your r here. Okay, your r times your current gives you your voltage. So that little piece right there is V little r. Okay. And then you go around, and then this part here is your big voltage drop from the armature. Okay, because it's a resistor, and then that's how much gets dropped from that. It's your same current that's going through there, since it's a series circuit, but this time the resistance here, since it's a big R, it's generally a bigger resistance than the internal. This is going to be your voltage drop through the armature, and then you're also going to have, from that movement of the flux, some back voltage that's working kind of against your current. Okay, and that's going to cause another voltage drop. So essentially you have all this juice coming from the battery. It's going to drop a little bit of voltage there, drop more voltage there, and drop some voltage there. Okay, so the formula they come up with is your back voltage is just equal to this minus this minus this. Or essentially, this is equal to this plus this plus this. But overall, all you need to know is this boxed one here. Your back voltage is your source voltage. Generally, they say your terminal voltage here is just what that is. Okay, so it's just the source voltage, or the EMF minus that little internal resistance, minus this voltage drop from the armature. Okay, and then that's what your back voltage should be. Okay, so that's the equation to come up with back voltage. Okay, so this is where Vs is, essentially that. Okay, so that's the circuit, that's the equation that we need to know. All right, so we'll see some questions with that in the practice. And then our last piece is, what is a transformer? This is it looks complicated, but it's a pretty simple equation, and it just kind of tells you what a transformer is, what it does. Okay, so generally an example here, or you hear about transformers, is if you have high voltage wires coming from maybe BC Hydro, producing tons of power, really high voltages, and they get transported over to Chilliwack, and then essentially it goes through a transformer, generally a series of transformers, more than one of these, but we'll just say one just to simplify it, and then it'll take that, it won't give you that super high voltage of say 500,000 volts, and it'll essentially bring it down to your house voltage, which is 120 volts. Might be 240 volts, depends. But essentially the voltage has to get dropped a lot because it's dangerous to have that high of a voltage in a house. So they use this thing called a transformer. What is it? It's just this iron core with loops of wire around two sides like that. They call this one side the primary side, this side the secondary side. You can see it's two circuits. You have one circuit here and one circuit here. And due to the magnetic field that happens in this core, essentially the number of turns in your primary side divided by the number of turns in your secondary side gives you a ratio, and that ratio essentially tells you how much the voltage changes from here to here. Okay, so all you have to do is control the number of turns you have around this core, and it'll tell you how much you want the voltage to drop or increase. So here is the overall equation. Number of turns in your secondary divided by number of turns in your primary will tell you your voltage in your secondary over your voltage in your primary. Okay, so if you wanted to drop it from 500,000, you'd essentially want your number of turns of primary to be more than the secondary. Okay, so if you have more turns over here, less over here, then it's going to drop the voltage essentially. Okay? But if you drop the voltage, you can see the P and the S are switched here versus S over P, S over P. This is P over S. If you drop the voltage down, that essentially increases the current that you have. Okay? So it increases the current if you drop the voltage. Okay? And that's another thing to worry about, because really high currents is what creates heat and essentially can create fires. So let's go through this really quickly. Transformers change very high voltage to a low voltage, or vice versa. So transformers are two solenoid loops. So there's one solenoid, there's the other. One called the primary coil, one called the secondary. If your number of primary turns is more than your number of secondary turns, that means you're decreasing the voltage, and vice versa. Alright, so if you're increasing the voltage, say you're going from here to here, that's called a step-up transformer, and then the other way is called a step-down transformer. One thing that's interesting is most things in this world are not even close to 100% efficient. So, like, especially if you're talking about cars and then using the energy from gas into movement, they're not very efficient. But when it comes to transformers, they're uniquely almost 100% efficient. They're usually seen as being 99% efficient. So the transfer of energy in these things are very good. So that's our equation we're going to use for any questions. And this essentially tells us the ratio. All right. Last page here, this is just kind of giving you an example here. You have a high transmission wire giving a 500,000 volts of electric potential from one city to the next, and it can travel at a current of 2 amps. Okay, that's how fast it's traveling, or its current. To get from this to a household voltage of just 120 volts, we would have to use a series of step-down transformers. We're going to give an example of where we just have one transformer. Okay, so our equation that we can get is ES over EP, or EMF S over EMF P, is equal to IP over IS. So our ES, or our secondary voltage that we want to get to, is 120. Our primary voltage that we're coming from is 500,000. Our current of our primary is just 2. So let's find out what our current of our secondary one. So 120 divided by 500,000. We have to essentially multiply by IS and then divide by that value, and we'll get an IS of 8,333 amps. This doesn't actually happen because that's way too high of an amp value for your house, because this is just one transformer, but they use a series of transformers to lower it kind of at a slower rate. So that would be theoretically the amps that would be going into your house. And that's it for the lesson. This link right here will tell you why they use super high voltages to transmit electricity over long distances. Because it turns out if you use low voltages, you lose a lot of energy to heat. But if you can transfer them in really high voltages, it turns out that you're way more efficient and you lose very little energy to heat in that way. All right, thank you.